Let us start our second day of well testing, advanced well testing by MS Excel, and today we are going to discuss about gas well. So let us start with our day with gas well testing. So for that, let us start one of the tests that will be conducted to estimate the best way how a gas can enter into the well. Like a well, every well has its own potential capacity to allow either oil or gas to flow through it, through perforations towards the wellhead. Like, what is that capacity? Like, every well has its own capacity. So the best capacity per day, how much gas can be produced? So that can be done through gas deliverability test. For that, we are going to take four random values of pressures. Based on that, we are going to estimate the flow rates. With that, we are going to estimate the best capacity of that well to produce maximum output of gas per day. So that is how we are going to conduct this test. For that, we need to allow well to produce for four different flow rates. Like we need four different flow rates. We need 4 points of flow rates. So why? Because we need to construct a line that will give us a slope. Based on the slope, we are going to extend towards the condition where we can estimate the potential capacity of that particular well. So for that, we need to construct a graph, x and y axis. That is like x axis, we have to take as flow rate of the gas at standard condition, and y axis is the differential square pressures. So PR square minus PW square, that is reservoir pressure square minus wellbore pressure square. So this is the value, this is the differential value. It is not the value of simply PWF. It is the difference between PR square minus PW square. So normally when we are doing it for oil wells, we are going to take simply PW. But when it comes to gas, we need more pressure difference, so that the more we can able to get equations with more pressure difference. Why? Because gas equations are not as linear as oil equations. So they were a little bit more complex. So because of that, we are going to take more pressure difference. So the drawdown is not about PR minus PW, but it is about PR square minus PW square. So the least value for PR square minus PW square will be 0. Means when PWF is equal to PR, the difference value will become 0. When both values were same, like PW and PR, if they both were same, then we cannot expect any flow rate that is coming into well. If the value of PWF is lesser than PR, then the flow will start. So if the value is minimum, like if PWF becomes 0, then the flow towards that well will be expected to be maximum. So the maximum value for y-axis, we can take it somewhere around here. That is PR square minus the minimum value of PWF, that is equivalent to 0. Means simply PR square. So it starts at 0 and it ends at PR square. In between is the difference between PR square minus PWF square. So let us take 4 different flow rates with respect to these pressure differences, and we will estimate 4 different flow rates. Like randomly, we have collected 4 different flow rates. So you can see these blue ovals are all different flow rates that have been calculated on the graph. So with respect to different differential pressures, we got these 4 flow rates. Like we have estimated 4 different flow rates. Corresponding to that, we got differential pressures. So these are the points initially it is required. So once these 4 plots were brought, then we need to attach these 4 points linearly, and we have to extend that line. We need to attach these 4 points linearly, and we have to extend this line until you reach a projected line which is equivalent to PR square. So somewhere around maximum value of y-axis will be equivalent to PR square. Why? Because PWF will become 0, then the difference will be equivalent to PR square. So you have to project a line from y-axis so that these both lines has to be intercepted. So we need the intercepted point on the projected line from the y-axis and the extension line from the points where we have overlapped on the this on the graph between QSC and PR square minus PWF square. Once they were intersected, then with that intersection point, you need to project it onto the x-axis. So this is the flow rate, which will be the maximum flow rate that the well can able to produce. So it could be of any number. So that flow rate, we are going to name that as AOFP, that is absolute open flow potential. So before conducting this test, the well has to be allowed to produce for 4 different flow rates corresponding to 4 different pressure drops. So these 4 flow rates will be linearly connected with a straight line, and that straight line will be extended towards a projected line from the y-axis, that is PR square. Once they were intersected at somewhere in the graph, from that intersection point, you are not going to write, you're going to draw a perpendicular line from that towards x-axis. So the point where exactly it is meeting on x-axis is the maximum flow rate of that particular well to produce gas. So it could be of any number SCF per day. So the same graph, it was over here. So you can see that 4 points were there. They were projected it where the PR square is here. So the PR square projected line is this. Both were intersected, and intersected points from there you have they have like actually projected towards x-axis. So here we can see it is a logarithmic graph, like 1, 10, 100. So it is in between 10 and 100, and the units were mentioned to be SCF. M represents 10 power 3. So 10 power 3 plus into 10 power 3, that will be 10 power 6 SCF, standard cubic feet, and a D represents day. So it could be a number between 10 and 100, probably 20 or 30. So 20, let us take it as 20. So 20 SCF, 20 into 10 power 6 standard cubic feet per day. So this is how we can able to estimate the best maximum flow rate of that particular well by taking 4 different random points. So this is how we are going to do this test. So this will be done by graph, but there is another way to estimate AOFP. So that is like, this is the formula to estimate AOFP is equal to C, which was coefficient, into the condition for AOFP is PW should be equivalent to 0. So once it is 0, then C into PR square whole power n. So if you know the value of PR, C, and n, we can estimate the value of AOFP. And C can be estimated as any flow rate by its pressure differential to the power of n. N is an exponent, or else it can be taken as a slope of these 4 points linear line. So how to estimate n? 1 by n is equal to log PR square minus PW square. Either like you can take 2 points, one this point, any of these points from this 4, like 2 points you have to take slope from that. That will be giving you the value of n. So if you know the value of n, C, and if you put it in this equation, we can able to estimate the value of absolute open flow potential for that particular well. So this test will be helping us to understand the best possible way of producing maximum amount of gas, that is in standard cubic feet per a limited time. It could be days. So mostly it will be measured with respect to days. So this is how we are going to estimate gas well gas deliverability test. Then if you come towards hydraulic fracturing, we have 2 different ways to approach. One is, first of all, we need to indicate that the fracture is present inside the reservoir. So how to estimate a fracture, whether the reservoir carries fracture or not? So that can be done by pressure buildup test. In our last class, we have discussed about pressure build-up test. So how it can be estimated, how the build-up curve will be generated. There are two graphs that have been superimposed, and based on that, we have estimated pressure build-up. But if the graph looks like this, then it indicates that there could be a chance of natural fractures which were present inside the reservoir. So what are the indications for that? Same way, pressure build-up test, that means the pressure will start to build up, but suddenly it will deviate, and again it will attain its same slope. So you can see two parallel slopes on one graph. So if there were two parallel slopes that were observed on one graph, then we can understand that there is a chance of fracture, that too a natural fracture, not an artificial fracture, but it is a natural fracture. So that have been generated inside your well. So it was already present over there. So the same way how we conduct pressure build-up test, that will be done. Delta P, which is logarithmic delta P versus bottom hole pressure, shut-in pressure. During shut-in, pressure will start to build up. It raised up and it took a deviation path, and again it has attained its own slope. So we can able to get two different slopes, and these two different slopes will almost be same, like they will be having the values almost similar to each other. If that is the case, we can expect that the reservoir is having a fracture. Then comes hydraulic fracturing. So this is a technique to increase the productivity of a well. Normally, reservoirs will not have enough channels to produce any kind of fluid that enters into the well. So for that, we need to, this is a technique that will be done most oftenly in low permeable reservoirs, so that the channels will be increased through fractures, so that more space will be generated where the flow will become easier and smoother, and that will start to move towards your production. So this is an artificial fracture that is going to be generated by injecting fracturing fluids. So fracturing fluids is a technology, like it depends on the formation. So how a fracturing fluid has to be designed or synthesized. It could include drilling fluid, I mean, like water, sand, everything which is connected with reservoir fluids. Apart from that, some other chemicals will be added to that, so that it will start entering into the formation and it will create a fracture. So once the fracture is generated, then the fluid will start to move even more smoother than the channels which were present earlier. So how it can be observed? Like if you start injecting fracturing fluids into the reservoir, then there is a process to understand how this fracture is started to, and this will be done through formation integrity test. And you can see there is a graph which was kept over here, and this is the formation, the layer which was in this form is a formation layer, and this as well. If perforations were done, and the channel will be generated, and we are going to inject fracturing fluids like this, so it will start entering into the channel. So right now the condition is fracturing fluid is entering into the channels which were generated by perforations. So perforation itself will create a channel, but the flow is not enough through this channel. You can see very narrow channel that was generated over here, and we started to inject fracturing fluid into these channels. Once the fracturing fluids entered into this channel, the pressure is expected to rise up. So from here onwards, the pressure is zero. It started to rise up. It will go on rising up until it creates one particular slope. So up to here, the slope is almost linear. Then after reaching here, it will start to deviate towards right side. So that means this is the point where the fracturing fluid started to enter into the formation apart from the channels that have been already created earlier. So up to now, it was entering into channels. From this point onwards, it will start to move. It will pressurize the formation space which is around these channels. It is going to fracture, but it haven't created it. but right now it started to move into the fractures. Because of that, the pressure will start to little bit deviate. So it will start to deviate from the slope towards right side. So that particular point we name it as leak off point. So this fluid, fracturing fluid, leaks into the formation from the channels. So until leak off point, the formations haven't gone through the sorry, the fluid haven't gone into the uh, formations. But right now, it has reached towards a pressure where fluid started to enter into the formations. Because of that, there could be a change of slope from here onwards. So in that way, still the pressure will rise up until it reaches for fracture breakdown point. So this is the point where it will create a bigger fracture suddenly, like a small kind of fracture it will create over there inside the reservoir surface. So it is an empty space that was generated by the fracturing fluid. So it started to enter into the channels and it reached to leak off point. After leak off point, still the pressure have raised towards a level where the formation couldn't handle it. Because of that, there is a small fracture, bigger fracture from the channel that will be generated. That is the point we name it as fracture breakdown point. So from this point onwards, you can see the space over here is high. I mean, compared to the volume of this fracture is more than the volume of the channel that was generated by perforations. So because of that, the injected fluid pressure will be less than the fluid which is flowing through this I mean empty space. Because of that, the pressure drop from FBP can be observed. So this FBP is the point where fracture breakdown point will be generated. After that, the fluids will move smoothly into the empty spaces of the fracture, making the pressure to get reduced. So it will start to reduce and finally it will take a stable point. From that point onwards, the pressure will be maintained constant towards some time. So this stable point, we are going to name that point as fracture propagation point. So this is the point where the fluid will flow through that fracture. So the fracture has a pressure that is a constant pressure. That pressure will be constant, where it will allow fluid to flow through some time into that particular space. So that pressure we name it as fracture propagation pressure. So after that, we have to stop injecting the fluid. So this is the time where the fracture propagation point will also start to reduce pressure. Why? Because the injection pressure have reduced. Then the pressure at fracture propagation point also will start to reduce for some extent, a little bit. That point we name it as initial shut-in pressure. You can see there is a point called ISIP. So that is initial shut-in pressure. This is the pressure created at the shut-in condition. Shut-in means we are not injecting. So injection have been stopped, but still the fluid is present inside the fracture. So this point is very important to understand the potential capacity of a fracture. So right now, the fracture was stable without any injection. The fracture was maintained in its own way. So there is not, this is the potential of that particular fracture to maintain its space so that fluid will start to flow through it. So that also will take some more time. So initial shut-in pressure will take some time, and after that it will start to decline suddenly. So abruptly we can understand this fracture will start to close, but it will take some time. So the time is very important over here to understand the potential capacity of that fracture to attain some time so that the fluid can be flown through that for some extent. Then after that, the fracture will close. So once the fracture closes, then the fluid which was present inside will be displaced through towards the formation. So here they have mentioned it as bleed off. That represents the fluids inside the fracture have been displaced. That means fractures have closed. Then the pressure will be dropped towards its normal. So this is how the process of injecting fracturing fluid and how the fracture will be generated, how much time the fluid have been stayed inside the fracture without injecting pressure. So the difference between ISIP and FCP. FCP is the point before closing the pressure, like before closing the fracture. So after reaching FCP, the pressure will be dropped abruptly and finally it will attain its own position. So the time taken from ISIP to FCP is the potential capacity of that fracture to withhold in that formation to allow fluid to flow through it. So if the time is more, the production through that fracture will be more. If the time is less, then the production through that fracture will be less. Production through that fracture means more amount of fluid can be produced with more volume of that fracture. So this is what it happens at the first cycle. Then after that, if you repeat the same test, the same way you can able to see that the slope it has been attained, but right now there won't be any fracture breakdown point. It will be having already fracture have been generated and there is no new fracture that will be generated in the second time. You are going to inject the fluid in the same location so that earlier fracture which have been closed, again it will reopen. So this FRP represents fracture reopen point. So in first cycle, we created a fracture and in second cycle, we reopened that fracture. If you could observe the same graph over here, you can see ISIP, which is initial shut-in pressure, to FCP, we have some time, but the second time, the time difference will be more. So that means when you do the same process once again, the time difference between ISIP and FCP, ISIP means initial shut-in pressure, to FCP means fracture closure pressure. So that in the second cycle, you can observe that the time scale in between FCP and ISIP was observed to be more. That means it is attaining more time. In that way, it can able to produce more amount of crude oil through it. So if you could repeat second time, then the fracture attainment and potential of that fracture can be increased. Based on that, we can produce good amount of crude oil. So let us start to observe this in Excel, how Excel will help us to understand. So first of all, we have discussed about gas deliverability test that has another synonym, that is flow after flow test. So if a flow after flow test was performed on a gas well located in a low pressure reservoir, using the following test data, determine the values of N, which is exponent, and C is coefficient for the deliverability equation. And AOF, sometimes it will be called as AOF, absolute open flow, or else AOFP, absolute open flow potential. And flow rate at particular pressure, which is equivalent to 175 psia. And the data was given over here, that is QSC, that is the flow rate, and the first value was observed to be 0 at PWF is equal to 200, and after that the pressure started to reduce. Theoretically, we can able to estimate the value of AOFP, that is what they were asking. So we can, if you know the value of C, N, and PR, and we can get the value of AOFP. So if you want, if you have to estimate the value of C and N, these are the formulas, and C is equal to QSC by this is the formula, and N means you have to take the values from this logarithmic, then we can get the value of N, then we can estimate the value of AOFP with these two values. And QSC for a particular pressure, that is if the value of PW, if you have given as 175, then we can get that flow rate. So this is the question for the gas deliverability test. And here the value of PR was not given. If you could observe in this data, the reservoir pressure value was not given, but there is a clue that was given is flow rate was observed to be 0 at PWF, which is equivalent to 200. When PWF value is 200, flow rate was observed to be 0. This happens when the reservoir pressure, when PWS is equivalent to reservoir pressure. That means this value is directly equivalent to reservoir pressure. If PR square minus PWF square is equal to 0, then there is no production. Why? Because both values are same. So when there is no pressure difference, there won't be any production. So that means PWF is equal to PR when QSC is equal to 0. That means this is the value and of reservoir pressure. So 200 is the value for reservoir pressure. So this is the problem that we are going to do it through two different ways. One is theoretical and another one is graphical. And let us see how we can able to estimate AOFP by these formulas. And we will use Excel to estimate the same thing, AOFP. So these are the two steps we are going to do it for gas deliverability test. Then detection of natural fractures by the raw data which have been already given. As earlier we have done pressure drawdown test, we have understood the slope, and right now we need two values for that. One is shut-in time to estimate fracture and wellbore pressure. So these two parameters are required to estimate fracture. And when it comes to hydraulic fracturing, we need time for injecting, that is product, injection time is required, and then the pressure corresponding to injection time that has to be recorded. So I have taken this whole data to Excel, and let us go to Excel and try to solve the AOFP, and we will try to analyze the fractures. So first of all, we are going to discuss about the values of AOFP. So I have given the formulas over here, the same formulas, C 1 by N QSC AOFP. So if you know the value of C and N, we can able to understand the values of, so we can able to estimate the value of AOFP. So before that, let us go with graphical first, and then we can come to theoretical. So for that graphical, we need a graph between PR square minus PWF square versus QSC. So we have QSC, we have PWF, and we need to generate PR square minus PWF square. When the value of PWF is equal to 200, QSC value is observed to be 0. That means here PR is equal to 200. So if you want to get that value, I can give PR square minus PWF. So all the PWF values were over here. So what I'm going to do is the first value is equivalent to PRs, and we need PR square. So I'm using the term like this. The term of the first one power 2 minus the same term power 2. So I got the value as 0, but this value is constant. So I am making that as constant by giving dollar symbol. Then after that, I will iterate it further. So this is the difference between 200 square minus 196 square. And the next one is the difference between 200 square minus 195 square. And then 200 square minus 193 square. So this is the pressure differential between PR square minus PWF square. So we have right now y-axis and we have x-axis. So x-axis should be always on left side. So I'm going to start inserting a graph. So I got a graph based on PR square, which is on y-axis, and x-axis is QSC. So right now, as per the theory that we have discussed in the presentation, we need to project our linear equation towards a straight line which is equivalent to PR square. So you can see PR is 200. So what will be PR square? So that will be is equal to simply 200 square is 40,000. So we need to extend this equation until you reach y-axis 40,000. That means we need to adjust first y-axis. So I'm going to give the limits for y-axis minimum as 0 and the maximum to be 40,000. So I will make it as 50,000. And if I give it like that, then you can see that the y-axis limit started from 0 and it has been ended at 50,000. So we are supposed to get a projection from 40,000. So I'm going to insert a straight line and just extend this graph. This is the point where we are supposed to project it. So how we can able to project this these are the 4 random points that have been generated. I'm going to insert a trend line, so which will give me a linear slope of this 4 points. The last one is 0, so that cannot be considered completely. So the 4 points which we have generated, based on that we are supposed to estimate the slope. And right now we need to extend this trend line so that it will meet the line which is projecting on y-axis, that is 40,000. So why 40,000? 40,000 is PR square. So that is how we have to reach until that. For that, I'm going to just format it. So what I'm going to do is I'm going to forecast forward set. So forecasting forward means that extension of this line. Excel has an option to extend based on the slope of this linear line. So if I extend it up to 1,000 units on x-axis, so it started to move forward. So in place of 1,000, I'm going to use 10,000. So it started moving up. So we are supposed to reach 40,000. So we are still here. So let me have 25,000. So still we are moving up. Then 55,000. So we almost reached near to 55,000. You can see that the projection from 40,000 is intersecting towards the extended trend line from the linear axis. So this linear line have been extended through a trend line that have intersected on the projected y-axis, that is PR square. So projection line also I will give. Yes. So this is the extended projected line from y-axis, and that both have been intersected. I'm going to just highlight that. So these both have intersected at this point, and we need to project that towards x-axis, and it is coming almost equivalent to 60,000. So 60 MSCF per day. So that is the value we are getting it from graphical side. So you can see that the value coming from the projected intersected line towards x-axis is coming almost equivalent to 60,000 standard cubic feet per day. So this is how we can able to estimate the value of AOFP. The value of AOFP for this graph is 60,000 standard cubic feet per day. So this is the value how we can able to estimate for AOFP. I'm going to put this value as AOFP through graphical method. So the same thing we are going to do that in theoretical way. Let us keep this graph beside. And I'm going to do for theoretically, we need a few values. That is, first of all, for getting AOFP, you need C, N, and PR square. So for that, what we have to do is, first of all, let us try to estimate 1 by N. So 1 by N is log PR square minus PW square. Any point, it is 2 and 1, probably this 2 and 1. We can take log PR square minus PW square, the second point minus the first point, by Q log QSC second point minus first point. So here log A minus log B was given. So we can take it as log A by B by log A by B. So that is what I'm going to do. I'm going to get the value of 1 by n as, here we already have numerator values PR square minus PW square. So I'm going to take simply log, second point, I'm taking this log, second point, that is this log A minus log B, that can be taken as log A by B. So by the first point is PR square minus PW square corresponding to the first one. So this is the blue one is second and the red one is first. So this completes my numerator. By, when it comes to denominator, the same thing, log bracket QS2. So the blue corresponding QS2 is this one. Log A minus log B, I can write it as log A by B by the first one, 2730. So we got the value of 1 by n as 0.5. So if you want to get the value of n, then the value will be equivalent to 1 by of this point. So that is 1.69. So we have the value of n. If you have the value of n, we can get the value of c by taking any point of these four and we can put the value of n here. So QSC, I'm taking the second point. So that is equal to QSC. Second point is 3970 by bracket. Corresponding to that, PR square means PW square is this power n, that we got it. So we got the value of C to be 0.01011. So we have the value of C, we have the value of n, and we can estimate the value of AOFP. So theoretically, AOFP can be given as C into PR square power n. So C value was given into PR square. So PR square here we have written already. That is this into power. This, for PR square we have power n. So we are getting 65,521, something like that. So we have 60,000 here. 61, 2, 3. We have 65,000, something more we have it. So probably it could be of 40,000 is the error. We have a little bit more error. We got it over here. So almost it is coming big error only. Just we should get the values with respect to five tens. 60,000 means we have to get the value which is corresponding to 60,000. And we are getting 655,219, which is bigger in number. So here log A by log B, everything is correct only. Okay, what I will do is I'm going to just change the Q2 value to be the last one. So just I'm changing not the second value, but I'm going for the last one since we have only 4 data. So corresponding to that, even if I change QSC value also, so PR value I changed to the last, and this value QSC also I'm changing to last. Let me see. Yes, this is coming close to the number what we have got, that is 60,000. So the second one is according to theoretical formula, it is not coming. Probably this could happen by considering more amount of points. When you are taking close points, we cannot able to get the estimation point which was showing at the top. So you can see if I could consider the last point like 4 points, but the reduction will be more. So since we are moving in the reduction side, then the value will be coming close to the estimated value of 60,000. But here The second point is having very much less in reduction. So the estimation value, we are not getting close to that. So this could be the reason why we are getting a larger error if you are taking the second point. But if you could take all the points, the last to first, then we are getting something close to the numerical value, which is equivalent to our AOFP. So this is the AOFP. We got it through graph. And this is the value which we got it through theory. Why we can't consider the second point? It is not like that we should not consider the second point, but sometimes the difference in between these 2 points is not enough to predict what we are predicting, what could be the accurate value. So because of that, we have to go for the last point according to the graph, and we have to start predicting it theoretically. So in that way, we can estimate AOFP. Then if you start moving towards hydraulic fracturing, so first of all, we need to start generating a graph, that is pressure buildup graph. So this is the data that we have, that is TP plus delta T by delta T, and delta T PWF, which the fracture was generated by these pressures, and then T is the injection time and the fracture. So this is the injection pressure. So let us try to see what are the things that we can able to estimate from this graph. First of all, we have to start constructing pressure buildup test. So that is TP plus delta T by delta T versus PWF. So I'm going to take this form, that is y-axis, and this form, which is on x-axis. So y-axis is TP plus delta T by delta T, and x-axis is PWF. Let us see how we need a parallel line to understand this, that the reservoir is having fracture. So we are getting some random graph. Since the x-axis was not mentioned with respect to logarithms, because of that, we couldn't able to get a proper trend of that graph. So I'm going to just format it x-axis to logarithmic values. So I'm including logarithmic values. So you can see right now, there are 2 different slopes, and there is a region where these 2 slopes have been generated, and this can be observed only with respect to logarithmic graphs. So if this is the condition, we can understand that the reservoir is having natural fractures. So let us try to understand the slopes for these things. So let us take the point which is starting, that is x-axis 9.8 and to 45. So which is x-axis. So 9.8 to 45. 9.8 to 45. So this is the points we are supposed to take, and corresponding to that, the fractures, sorry, pressures we are going to take, and we are going to see the slope for that. So the green one, we're going to estimate the slope for these green shady areas. These points correspond to the line which started from here and which has ended here. So we are going to estimate the slope of this straight line. So slope and known y-axis. So y-axis doesn't have logarithms. So y-axis is this, comma. When it comes to x-axis, we have logarithmic values. So x-axis, we are going to use log of these values. So we got slope as minus 34. So we got the slope as minus 34, that is y-axis, and which is x-axis we got. So let us try to see the same slope value, the same values like that for these points. From the point attained from here, why? Because this looks little deviated. From here onwards, we can observe that the constant slope have been generated, and after that also there is a deviation. So we can take the points from here, that is 90 to 597. So 90 to 597. So 90 is this one and 597. So these are the points we are going to estimate slope. Slope known y-axis, so that is this, comma, and we are going to use log for the x-axis. These are the points for that. We got minus 40.476. The thing is, these two slopes are almost coming close to each other. It cannot be exactly same, but probably 5 to 6 or 7% error will always be there. So if the slopes were almost same, the only thing is we need to avoid some points which were deviated from the original points. Because of that, there could be some error. So, or else the answers are coming almost near to equal. So we took only the points which were coming close to the trend. So because of that, the error was observed. But most oftenly, these answers can be considered that these both will be having a similar slope where it can result a natural fracture. So this is how we can able to estimate. But based on these slopes, we can able to estimate that the reservoir is having a natural fracture. Okay, this is the one we have created to understand whether the reservoir is having natural fracture or not. Right now, we are going to see after injecting fracturing fluid, whether the points have been generated like leak of point and all this through hydraulic fracturing. So this is the injection temperature, sorry, time, and this is the injection pressure. So I'm inserting the graph. So we have got the first one and the second one. So we can understand based on the graph what we have discussed. In the presentation, we got, compared to that, we got a little bit almost similar over here. So this is the one where the fractures were generated, and this is the graph of hydraulic fracture. So I'm going to extend it to understand even more clear. So we can see how the points have been distributed. So initially during injection, the slope it started to attain, and it has reached towards a point where the slope started to deviate towards right side. From this point onwards, it started to deviate towards right side. So this point is what we can name it as leak off point, LOP. So I can just insert a shape. So from this point onwards, you can understand, you can see that the slope which have, okay, these are the points which are not equivalent to the slope what we got it here. But the thing is, these are deviated points, probably because of either skin effect or wellbore damage. Some deviation will always be there until some time. Then after that only, it will start to attain its constant slope. Once you reach towards a point, then after that, if it starts deviating, then we can understand that we reach to leak off point where the fluid started to enter into the formations. Then it will take some more pressure to reach to breakdown point. This is fracture breakdown point. After that, the pressure will drastically falls down. So this is the point where the bigger fracture have been generated. So this point we name it as fracture breakdown point. So here is the point where we can name it as fracture breakdown point. So we can indicate that as fracture breakdown point. Fracture breakdown point, FBP. Then after that, FBP, it will start to reduce. Why? Because right now the condition is fracture volume was higher and the injection pressure is not enough. So whatever injection we are giving through the injection well, that pressure is not enough to maintain the flow which was present inside the fracture. So the fracture volume was more. Because of that, the pressure which was observed inside fracture will start to get reduced until it attains a constant constant pressure. So this constant pressure indicates that the pressure, with that constant pressure, fluid can be flown through that fracture. Whatever amount of fluids we are injecting, that attains a constant pressure and it will start to move in that fracture with that constant pressure. So that starting of that constant pressure is fracture propagation pressure. So that also will start near to here. Then from here onwards, you can see all the points are almost going in a constant way. So this is fracture propagation pressure, FPP. And then once you come close to the end of constant pressure, we have to stop injecting it. So once you stop injecting means you are not giving additional pressure to that. This is what we name it as shut-in condition. So from here onwards, shut-in condition starts. So this is the point initial shut-in pressure where the pressure have reduced because we are not injecting fluids, fracturing fluids right now, but still the fracture pressure was maintained for some more time. So it started at initial shut-in pressure and it has moved until it reaches fracture closure point. After that, the pressure will immediately drastically goes down. Why? Because this is the time only we can able to maintain fracture in that location for that particular time period. So you can see the time period. This is the most important part of hydraulic fracturing, the time period attained between ISIP and FCP. So I'm going to put that points ISIP, which is here, and FCP, which is here. So these are very important points, that this is the time gap between FCP and ISIP, which shows that the fracture is having potential to maintain without any artificial injection up to that. So this is initial shut-in pressure, ISIP. Initial shut-in pressure, and until it reaches fracture closure pressure. So fracture closure pressure, FCP, means the fracture potential have been completely gone. Then after that, because of formation pressure, overburden pressure, the fracture which was generated by your fracture fluid will start to close by bleeding all the fluids into the formation. Once the bleeding starts, that means like once the formation fluids which were present inside the fracture have been displaced, then the pressure will start to get reduced and finally it reaches its original pressure. So this is the second graph. After the first one, we have generated the second one. So you can see there is an attainment of constant pressures here. So this is the point we can name this as FRP, that is fracture reopening point. So there won't be FBP here. Why? Because already initially in the first stage itself, FBP will come, but the second phase we will not get FBP. We will be getting fracture reopening pressure. So that is the name. It will be given fracture reopening pressure, FRP, and we can understand that ISIP is here for the second one, and you can see the time gap between ISIP and FCP for the second cycle. So there is a lot of time which was maintained. That means the fracture have attained for longer period. So this is ISIP. This is the second cycle ISIP, initial shutting pressure. Then this is the final closure pressure for second cycle. So when it is compared with first cycle, the time gap between second cycle FCP and ISIP was observed to be more. So this is how stimulation works. So first cycle acted like a stimulant to the second cycle. Because of that, the time which was maintained by that particular fracture is more when it is compared with the first fracture that was generated by first cycle. So this is how hydraulic fracturing will help us to understand. So leak off point is the first one which will start at initial stage. Then we will be reaching to fracture breakdown point, then fracture propagation point, and then initial shutting pressure and fracture closure pressure. Then after that, in second cycle, we can get fracture reopening point and initial shutting pressure and FCP. So this is how formation integrity test will make us to understand uh, how hydraulic fracturing works and how it can attain for longer period, how the fractures can be attained for longer period. So with that, this is the one we are going to close our session by these two graphs.